These are the findings that I made for my Robotics Project 1 RVM1 Manipulator forward kinematic equations. So the RVM1 is a 5 degree of freedom manipulator. So you can see here, right, so this is a 3D model that I created using Autodesk Inventor. The joints are actually all different revolute joints. So these are the different rotation assignment. So let me show you the 3D model that I have created. Okay, so let's open Inventor. So this is now the 3D model that I have created. Okay. All right. So let's just adjust the view. Okay. Alright, so this is the base, then you have the waist here. So the way the waist moves is that it is actually just doing this rotation. Okay. Now for the upper arm, alright, so that's the shoulder. For the elbow, okay, right, and then your wrist pitch, and then your wrist roll. So the end effector will be moving together with the wrist roll. Okay. Okay, assuming that this is the view of my end effector. So if you noticed, you will be only able to see two axes. Okay, the third axis, which is represented here as a dot, that means that that axis is going out of the page. Okay, so the third axis is actually pointing out, either going out of the page or going into the page. Okay, so you see, that is actually, okay, so let's assume that this is the sorry, the position of my, or the view of my manipulator. Okay. Alright, so with that view, I'll be able to, or I created now my coordinate frame. So we will be following the DH coordinate frame guideline. So first, the Z0. Okay, so for the coordinate frame guideline, it says that the Z-axis or the ZI axis is assigned along the axis of motion. So we saw earlier that the axis of motion is actually going this way for the waist. So that means that the Z-axis or the Z0 axis will be going on that motion. So that is why we have the Z0 axis going up here. Okay, so since this is the first coordinate frame that I'm going to create, or the zero coordinate frame, then there is no Z-1 or I-1 direction or coordinate frame. So I'll just assume my X sub O to be going here, and then following the right hand rule, then that means that my Y sub 0 is actually going out of the page or going in the page. Okay, so with that, I also assigned my origin 0 here. Okay, so this is now my zero coordinate frame. Now moving forward to the next joint. Right, so again, the ZI axis, okay, this time this is the Z1 axis, is assigned along the axis of motion of link I+1. So this is the link. This is now my joint. Okay, so which means if we look at the 3D model, right, so if this is now the movement of my waist, that means that Z is going up. My shoulder here, this is the movement. So this means that this is the movement, then the Z will be going out of the page. Okay, so that is the direction of my Z. So that is why Z sub 1, you won't be able to see it here. Okay, Z sub 1 is actually going out of the page, right? And then for the x-axis, so if the Z sub 1 and the Z sub 0 axis intersect, so the Z sub 1 again goes out of the page, then your Z sub 0 is, if you extend it here, they are actually intersecting. So the x sub 1 axis will be determined by the common perpendicular. Okay. Right, so this means that if Z sub 0 and Z sub 1 is going out, then X sub 1 will be at this location. Okay? And then following now the right hand rule, I have set that y sub 1 is going up. Okay? Now for the origin of your x sub 1, y sub 1, z sub 1 coordinate is at a place where the z sub 0 and z sub 1 intersect. Okay, so z sub 0 is going up, z sub 1 is going out of the page. They are intersecting here. Thus, we set the origin 1 at this point. Okay. Next, we go to the second joint. So for the second joint, again, we look at the direction of motion. So it's actually the same as your joint 1. Okay, so the direction of motion is also going at this way. Okay. So that means that z sub 2 is all again going out of the page. So z sub 2 going out of the page. Then we look at z sub 2 in reference to z sub 1. So they are actually parallel to each other. Okay, so z sub 2 is parallel to z sub 1. So in order for us to get x sub 2, we look at the common normal. Okay, so we connect the two of them, and then this is the common normal. So we extend, x sub 2 is going to this direction. Then, using right hand rule, we are going to get now y sub 2. For the coordinate of x sub 2, y sub 2, z sub 2, since the z sub 1 and z sub 2 are not intersecting, then we look at the common normal. Okay, so the part where the common normal and the z sub 2 intersects, that is now my origin 2. Okay, so that is why we have origin 2 here. Okay, so that is for the third joint. Now for the fourth joint, okay, again, the direction of motion is also the same as the previous two joints. So it's going at this way. So that means that z sub 3 is actually going out of the page. Okay, so z sub 3 is going out of the page. Okay, again, z sub 3 and z sub 2 are parallel to each other. So we look at the common normal. So this is the common normal. We extend it here. Then x sub 3 is located there. Okay, using right hand rule, we have now y sub 3. Okay, now for the origin, since z sub 3 and z sub 2 are again parallel with each other, we look at the common normal, the intersect of the common normal and z sub 3, and this is now origin 3. Okay, now for the fourth joint. Okay, so this is actually my fourth joint. So the axis assigned, okay, for this one, since the fourth joint is the wrist roll, the movement is actually different from that of the previous joint. So if you look at the 3D model, okay, so the previous ones, they're actually moving that way. Okay, but for the wrist joint, let's see, let's have a better view. Okay. So if you try to move okay, so this is actually the movement of your wrist joint. So with this movement, okay, we are able to assign that the z axis is actually going on the movement of motion. Okay, so this means now that for the z sub 4, the direction of your axis is actually here. Okay, so that is the direction of your axis, so z sub 4. Now for the x sub 2, we look at z sub 3. So z sub 3 is going out of the page here, and then we have z sub 4. So they are intersecting. So what is the common perpendicular of these two? So this is now my x sub 4. Okay. Then following the right hand rule, y sub 4 is going out of the page. That's why we don't see y sub 4 here. Okay. Now why is it that my z sub 4 and x sub 4 coordinate is placed here at this same origin as origin 3? Okay, that is because of the fourth rule, wherein the origin of the x sub 4, y sub 4, z sub 4 coordinate for this link is placed at the intersection of z sub 3 and z sub 4. Okay, so this is z sub 4, z sub 3 is going out, so this means that the origin is here. So I'm going to transpose or transfer the axis or the coordinate axis to this point. Okay, so that is why origin 3 is also the origin 4, and then you have here the coordinate system. Okay, for the end effector, right, I actually just followed the coordinate of z sub 4. Okay, so based on here, I'm going to place the z sub 5 at this direction, so it's actually the same as my z sub 4. Then the z sub 4 and z sub 5, they are in the same, they are actually somewhat parallel, so they are actually in the same line, so which means a common normal, I'm going to set it for x sub 5. Okay, then y sub 5 is going out of the plane. For the origin, then the intersection of z sub 5 and the common normal, okay, or common perpendicular. So that is now my DH coordinate frame, or that is how I derived the DH coordinate frame. Okay. Now for the structural kinematic parameters. So first, let us look at A sub 1. Okay, so it says that it is the distance from the origin. Okay, so that is now my origin of the first coordinate frame. So this is my first coordinate frame, and that is my origin, to the intersection of z sub 0. So let me extend the z sub 0 and the x sub 1 axis. Okay, so this means that A sub 1 is actually 0. So there is no displacement. Now for the offset angle alpha 1. So that is the angle rotation about the positive x1 axis measured from z sub 0, okay, to z sub 1. So z sub 1 is going out of the plane. So assuming that this is now my z sub 1, right? So that we'll just be able to visualize it properly. So this means that that is the distance measured along x sub 1 from z sub 0 to z sub 1. So this is now alpha 1 is 90 degrees. Okay. For the joint angle, so that is the angle of rotation about the positive z0 axis measured from x sub 0 going to the positive of x sub 1. Okay. So there is no displacement for this, or this is actually, this might be variable. So that is now your theta 1. Next, for the link offset. So from the origin of the 0 coordinate frame. So you have here the origin, right? And then intersection of z sub 0 and x sub 1 measured along the z sub 0 axis. So that is now my distance 1. Okay, so it is equal to L sub 1, which is 152. Right, so these are the structural kinematics of my first coordinate frame. Now for the second coordinate frame, okay, so again, for the link length, the distance from the origin of the second coordinate frame to the intersection of z sub 0, so z sub 1. So z sub 1 is going out of the plane. Okay, so I just leave it here. And the x sub 2 axis. So this is now my x sub 2 axis. Okay, so we measure the distance from the intersection of z sub 1 going to this origin. So that is now link 2. So A sub 2 equals link 2, which is 250 millimeters. Okay, next, offset angle. So the angle of rotation about positive x sub 2 measured from z sub 1 to z sub 2. Right? So there is no angle or difference in angle because they are parallel. Thus, alpha sub 2 equals 0 degrees. Okay. For the joint angle, so that is from z sub 1, angle of rotation, going from x sub 1 to x sub 2. Okay, so that is now the angle of rotation. So that is also variable. So that is theta 2. Right, so d sub 2. So from the origin 1, okay, going to z sub 1, okay, intersection of z sub 1 and x sub 2. So there is no displacement. They are located at the same point. So d sub 2 equals 0. Next, for the third coordinate frame. Okay, so origin 3, looking at z sub 2 along the x sub 3 axis. So the intersect of z sub 2 and x sub 3, and then check the distance along the x sub 3 going to the origin. So that is now my link 3. So a sub 3 equals L sub 3, or link 3, which is 160 millimeters. Next, for the alpha, or the offset angle. So we look at x sub 3, and then we look at z sub 2 and z sub 3. So there is no displacement between them because they are parallel. So this means that alpha 3 equals 0. For your theta 3, so we look at z sub 2, and then x sub 2 and x sub 3. So that is now the distance between x sub 2 and x sub 3. So this is now also variable, so that is theta 3. Okay, lastly, so from z sub 2, okay, we look at now the displacement between z sub 2 and the origin of origin 2. Okay, so here, okay, there is no displacement. Thus, the d sub 3 is actually equal to 0 as well. Okay, the fourth coordinate frame. So we look at now the origin, and then z sub 3 and x sub 4. So there is no displacement. So a1 or a4 equals 0. Next. Alright, so we look at x sub 4, and then we look at the distance or the displacement between z sub 3, which is going out of the plane, and z sub 4. So there is actually a rotation. So to move z sub 3 to be equal to z sub 4, we have to move it 90 degrees. So alpha sub 4 equals 90 degrees. Okay. Then for the theta, so we have, or we look at z sub 3, and then your x sub 3 and x sub 4 rotation. So this is now your angle. So this is variable, so theta 4. Okay, so d4. So we look at the origin, okay, of origin 3. Then we look at z sub 3, which is going out of the plane, and then x sub 4. So there is no displacement. So d sub 4 equals 0. Lastly, for your x sub 5, or for your 5. So we look at the origin, and then from that origin, we check out the z sub 4, okay, and the intersect with x sub 5. So if you look at here, there is no displacement again. So a sub 5 equals 0. Okay, for the alpha 5, so we look at now the x sub 5, we check x sub 4, and then z sub 4, and then z sub 5. So there is no displacement. So also alpha 5 equals 0 degrees. Okay, next, looking from z sub 4, we look at x sub 4 and x sub 5. So that is also variable. Okay, so it moves now. That means that it is theta 5. Okay, last, so we have the origin 4, and then we look at z4 and the intersection of z4 and x sub 5. So they have a displacement between the intersection and the origin. So that is that length, which is actually L4 plus, or link 4 plus link 5. So D5 equals L4 plus L5. which is 72 plus 75, which is at 147. Okay, so to summarize the structural kinematic parameters, so we have here the structural kinematic parameter. So I have links now, links 1, 2, 3, 4, 5. So alpha I, okay, these are the values. AI, alpha I, these are the values, theta I, and then the DI. So this is now the structural kinematic parameters that I'll be using to create my equation or forward kinematic equation or my transformation matrix. Okay, so using now these parameters, okay, so I substituted the values of my link length, right? And then using these parameters, I'm able to create now my transformation matrix. So the transformation matrix from 0 to 1, this is now the value that I got, okay? So using this transformation matrix, I can now create, or I can now find the position of my point in my end effector. Right, so using this formula. Okay, now I'll be able to verify the coordinate frame and the structural kinematic parameters as well as the transformation matrix in the following section. Okay, so let's assume the following joint angles. So this is how the connection should look like. So with the angles configured, these are the angles configuration. Okay, all right, so going back to the code, so what I did was I got the used MATLAB, and using MATLAB I created a function that is going to get my structural kinematic the transformation matrix using the structural kinematic parameters. Okay, so let's go to MATLAB just to show. Okay, so this is the function that I created. Okay, so basically I use the revolute joint transformation matrix. Okay, and then MATLAB will be the one who will input the different variables here. Okay, so I created a program now. So from this program, I will just simply input the values. So these are using now the structural kinematics. So assuming now theta 1 is 0. Okay, theta 2 is 0. Theta 3 is also 0. Theta 4 is 90 degrees. And then theta 5 is at 0. Okay, so let me run this program. So from running, I got now the point at location 557 and 152. Okay, all right, so my end effector position is at 557, 0, x is 557, y is 0, and then z is at 152. Okay, so I will try to verify this now using geometry. So using geometry, okay, so again, this is how it or the robot should look like. So I have here, okay, so L sub 1, and then these are just aligned, okay, together. Okay, so this means that for me to get x, it is actually just L2 plus L3 plus L4 plus L5. Okay. For y, since there is no displacement in my y, so y equals 0. And for the z is actually just this length, so L1. So that is why using geometry, we got x equals 557, y equals 0, and then z equals 152. Now I want to verify this further. I installed the robotic toolbox for MATLAB by Peter Cork, so we can verify the structural kinematics also based on this based on the code of or the toolbox of Peter Cork. Okay, so again, the output of the manipulator should look like this based on the input variables. Okay, so let's go to MATLAB. All right, so this is now my code. So here you just follow. Okay, we have here the different link lengths. So L1, L2, L3, L4, L5. So with this link, Okay, so we are just going to create now the formula, right? So just follow this format wherein Li, okay, equals link of theta, the D, A, and then alpha. Okay, so remember that they are also in radians. So L1 equals, these are the kinematic parameters. So for the theta, you just place it here 0 so that the code will generate or will create a variable for that. Okay, so L1 0 pi over 2, and then 0 0 L2 0, 0 0 L3 0, 0 0 0 pi over 2, then 0 L4 plus L5 0 0. Okay, and then we're going to create a serial link, and then we plot the value. Okay, so this time I will change the angles here. So theta 1 is 0, theta 2 is 0, theta 3 is 0, theta 4 is pi divided by 2, which is 90, and then theta 5 is 0. So I will copy this and then just place it here. Okay, so I run my program. So now notice now that the angle is here. Is that one? So with that, we got the answer. Okay, so this forward kinematics will give me now the value. So this 5570152. Okay, so 5570152, that is the point. So if we look at the summary of the results using the three different process, so transformation matrix versus geometry versus the Peter Cork MATLAB robotic toolbox, they actually generated the same values. Okay, let's try another verification. Okay, last. Okay, so using the following joint angles, so we have 30 degrees, 45 degrees, negative 45, 120, and 90. So using these following joint angles, what will be the point at the end effector? So let's input these values. So if you go back to my transformation matrix, so again with this code, I simply just have to set the theta. Okay, so I'm calling now my transformation matrix here. Okay, so first is 30 degrees. Next is theta 2 is at 45 degrees. Okay, theta 3 is at negative 45. Theta 4 is at 120 degrees, and theta 5 is at, let me see, theta 5 is at 90 degrees. Okay, so I run my program. So I got now the value 401, 232, 402. Okay, so that is now the end effector position using my transformation matrix and the structural kinematics values. Okay. Alright, so let us verify this using geometry. So this is how the the manipulator will actually look like. Okay, so the waist moved 30 degrees, then the shoulder moved 45 degrees, then from 45 degrees it went down again, negative 45, okay, and then you have 30 degrees here, and then 90 degrees for your rotation. Okay, so drawing it, we have the following diagram. Okay, so your revolute joint here, the waist moved 30 degrees. Okay, so that is why we have here, and then the shoulder moved 45 degrees. Now to get the x coordinate, so what I need to do is to get this value. So to get that, that is actually L2 cosine 45, which is now this line, and then multiply that with cosine 30 to get the value of x. X here is L3 cosine of 30. Then for the x value, we have L4 plus L5 cosine 30, multiplied it again by cosine 30. So that is the value. For your y, that is now the L2 cosine 45 to get this value here. Then the y value is actually multiply it again with sine 30. Okay, the y value for this one is L3 sine 30, and the y value of this one is now L4 plus L5 cosine 30 multiplied it by sine 30. So that is the y values. For the z value, that is L3 plus L2 sine 45. Okay, for this link, there is actually no z displacement. Okay, so it is horizontal, so it is in parallel with your z axis. Okay, sorry, parallel with your y axis, so there is no z displacement. Okay, and then L4 plus L5 sine of 30. So this is now my end effector position using geometry. So using now the formula, okay, I got x equals 401, y equals 232, z equals 402. Okay, so this is my point. So this time I want to further verify it using now Peter Cork robotic tool for MATLAB. So again, this is how the manipulator should look like, okay, based on the angles that we have or that we gave. Okay, so going back, or let's open the MATLAB. So this is my RVM or code. So I have here now the theta angles. Okay, so 30 degrees in terms of radians is pi over 6. Then 45 is pi over 4, negative pi over 4. So 120 is 2 pi over 3, and then 90 degrees is pi over 2. Okay, so let's run this. Okay, running it gives me now this manipulator here. Okay, and then I have here now the XYZ values. So 401.9, 232, 402.3. Okay, so using the Peter Cork, okay, so it gave me this point, 401.9, 232, and 402.3. Right. So if you look at the summary of the results using the three processes, the values are actually the same. So using my transformation matrix, 401.9072, using geometry is also the same. Then using Peter Cork, that is 401.9. Okay, x is 232.0412. Then this is for using geometry, and then using Peter Cork's. Okay, so this means that we are able to verify the DH coordinate system as well as the structural parameters. Okay, so that's it for my report. Thank you very much, and be safe always.